Good morning everyone, and welcome to our tutorial, From Detection to Direction, an overview of sound event localization and detection. My name is Junwei, and today I'll be presenting with Dr. Yiling Tan, and we are from the Digital Signal Processing Lab at Nanyang Technological University of Singapore. So here's what we're covering today. We'll start with a general overview of what sound event localization, or SELD, is, to understand what it is and why it is important. Then, we'll dive into the core technical components that make up a modern SELD pipeline. After that, we'll discuss the practical challenges of implementing SELD for real-time inference on edge devices. Now, in the second half, we'll explore the exciting frontier of multimodal SELD, where we integrate audio with vision, motion, and even language. We'll then touch on advanced and emerging topics such as 3D SELD and data-efficient learning frameworks. Finally, we'll see how SELD can be integrated with complementary functions like sound separation and scene classification to boost performance. Alright, let's begin with our first section, which is an overview of sound event localization and detection. So what exactly is SELD? Now, as the name suggests, it comprises of two core actions: sound event localization, to determine where the sounds are coming from, and sound event detection, to identify what exactly is making that sound. Now, SELD performs this joint task, or both at the same time. So to do so, we combine the functionalities of two established subtasks. First is sound source localization, or more commonly referred to in this field as direction of arrival estimation. So this determines the location in which the sounds originate relative to the receiving device, in terms of both azimuth, the left-right angle, and elevation, the up-down angle. So second is sound event detection, or SED. This identifies the sound class, or what is making that sound. It also determines when the sound starts and ends within the received audio signal. Now, ultimately the goal of SELD is to provide robust environmental intelligence through audio. So just as how we humans can place sounds in space and identify what they are, we aim to replicate this intrinsic human ability through machines. And that, in essence, is the core of SELD. Now, to put it simply, SELD generates a comprehensive spatial-temporal map of an acoustic scene. For example, let's take a look at this illustration. This is how we humans can listen and say, hey, there's a dog barking to my left and an alarm ringing to my right and slightly above me. An SELD system is designed to automatically produce that same level of understanding. Now, this capability is important because, unlike traditional methods that might focus on specific sounds like speech or specific warning sounds, SELD is designed to handle a diverse array of overlapping sound events simultaneously. And this robustness opens up applications in a variety of fields. For example, in public safety and surveillance, it is not just about detecting a gunshot, but also instantly linking it to the precise location to guide swift emergency response, all without relying on invasive cameras. For autonomous vehicles, vision is critical, but it's limited by field of view and occlusions. Now, SELD can detect and localize non-line-of-sight warning sounds, like an approaching ambulance siren, and this will give the vehicle crucial extra seconds of situation awareness where visual sensors may fail. And last is biodiversity monitoring, which allows for non-invasive, large-scale acoustic surveys that automates the process of detecting and localizing animal calls to track populations over vast, dense areas. So here's a great example of that biodiversity application in action. The Rainforest Connection project repurposes old smartphones, turning them into a dense network of acoustic sensors in rainforests. Now, these devices will continuously monitor for threatening sounds like chainsaws or gunshots, and use localization to triangulate the source of these threats. And this helps to prevent illegal logging or poaching. Now, another powerful application is in smart cities. Here at NTU, we have developed an edge IoT acoustic sensor network that was deployed in residential areas. Now, each sensor runs SELD on device to classify noise sources, such as construction, traffic, or shouting, and estimate their direction. And this aggregated metadata provides city planners with valuable insights for better urban noise management. So this brings us to the key methodological shift in the field. As we just saw, early SELD research often used modular pipelines. We have one system for detection, maybe a classical machine learning model like a support vector machine, and a completely separate, traditional method for localization. So the fundamental problem with this approach is what we call data association. If your SED model, say, detects a speech and a dog event, and your direction of arrival estimation module finds one source at 30 degrees and another at 60 degrees, how do you reliably know which sound came from which direction? In a complex polyphonic scene with many overlapping sounds, this task becomes nearly impossible to solve. So this is precisely why the field has shifted towards end-to-end deep learning solutions. Instead of treating it as two separate problems, a single deep learning neural network learns to perform the joint tasks simultaneously. It learns the complex patterns directly from audio, and in doing so, intrinsically solves the data association problem. Now, this end-to-end approach is far more robust in challenging acoustic environments and can successfully scale to a large number of overlapping sound events. Now, this rapid progress didn't happen in a vacuum. A huge catalyst has been the DK's challenge, short for Detection and Classification of Acoustic Scenes and Events. This challenge introduced a dedicated SELD task in 2019 and has been a game changer. DKs provides public datasets, open source baselines, and a set of unified evaluation metrics. So this has fostered a collaborative ecosystem that has in turn driven many of the breakthroughs that we discussed. So the timeline here shows some of those key milestones. From the very first DK challenge in 2019, to the introduction of complex datasets with moving sources in 2020, the pivotal shift towards real-world data with SARS-22 in 2022, the move towards audio-visual SELD in 2023, and now the current focus on 3D SELD with distance estimation. So as we've discussed, the field has largely converged on end-to-end deep learning pipelines, and that will be the focus of the rest of this tutorial. So the diagram here provides a high-level overview of what a generic SELD pipeline may look like. Now, it all begins on the left with data collection. This is our strongly annotated multi-channel audio dataset. In the training phase, this data is fed towards a feature extraction block, which is where data augmentation can also happen. Now, these features are the input to our core SELD system for network inference. The model produces formatted outputs, which are then compared against the strong labels during the evaluation step. Once this training loop is complete, the resulting model can then be deployed for robust real-world applications like biodiversity monitoring or autonomous navigation. Now, for the next part of this tutorial, we're going to break down each of these components one by one. So let's move on to our second section, where we'll examine the core technical components of a SELD system. So as this diagram highlights, everything begins with the data. The first crucial component is our data collection, and by extension, our dataset. This involves both the multi-channel audio recordings themselves, and critically, the strong annotations or labels for these audio recordings. This means detailed frame-by-frame annotations of what sound events they are, and the corresponding directions. So SELD fundamentally relies on multi-channel audio. We need multiple channels to capture the subtle spatial cues, like the inter-channel differences in time, level, and phase, that are essential for any localization task. Now, in many benchmark datasets, the audio is captured using high-resolution spherical arrays, like this 32-channel Eigen mic, as you can see on the right. Now, for SELD research, this higher order audio is almost always downmixed into one of the two principal formats. The first is the microphone array format, or MIC, which uses the raw, unprocessed signals from a few capsules in a known geometry, most commonly a tetrahedron. Now, second, and the more commonly used format, is the first order ambisonics, or FOA. The raw signals from the tetrahedral array are often called A format, which are then mathematically encoded into the standardized 4-channel B format, W, X, Y, and Z. So this B format is a holistic 360-degree and physically meaningful representation of the entire sound field. So ultimately, the choice between mic and FOA comes down to a trade-off between practicality and performance. The mic format is often flexible to a wider range of microphone geometries and is therefore more practical for real-world hardware setups. However, as we'll see later, FOA-based methods have consistently produced better results in benchmark challenges, likely because the 4-channel FOA format explicitly encodes the spatial information into its channels, giving the models a significant head start. So the good news here is that the field is rapidly expanding to bring SELD out of the lab and onto the consumer devices that we use every day. So this includes research into binaural audio for wearable devices and even standard stereo audio, which is notably the focus of the DK's 2025 SELD challenge. So this overall aims to make the SELD technology far more accessible for everyday applications. So SELD datasets themselves can be broadly categorized into two main types, synthetic and real-world data. Synthetic data, which often dominated SELD research, is generated by convolving dry sound event audio with measured room impulse responses, or RRs. So this approach is like a perfectly controlled laboratory environment. It offers precise control over all acoustic parameters, from vibration time to the number of overlapping events. Now, on the other hand, we have real-world data, which is captured directly in authentic environments and is often considered the gold standard for benchmarking model generalization, because synthetic degeneration, no matter how sophisticated, often fails to replicate the complex real-world acoustic conditions. So the obvious trade-off here is that collecting and annotating high-quality real-world data is incredibly time-consuming and expensive. So let's quickly walk through the evolution of these datasets. First, we have the Tau Spatial Sound Events series from Temple University. So these datasets are foundational in the sense that they essentially define the SELD task for the research community. The 2019 version was the first official dataset for the inaugural DK's SELD challenge, featuring static sound sources, and in 2019, the series introduced the challenge of moving sound sources. In the following year, it increased the difficulty again by adding directional interfering sounds, that is, localized sounds that are present in the scene but are not part of the target class to be detected, forcing the model to become more discerning. So these were the go-to datasets for the first 3 years of the DK's SELD challenges. So running concurrently with DK's, we have the L3DAS, or Learning 3D Audio Sources. So these challenges were also pivotal in pushing the field forward. Their datasets, particularly L3DAS 21 and 22, focused on SELD within office-like environments, providing data in the FOA format. Now, a key advancement came in 2023 when the L3DAS 23 dataset provided simulated visual data of the rooms corresponding to the audio, effectively extending the task towards an audio-visual context. So the shift towards greater realism was first highlighted by these early, manually annotated real-world datasets. The SELD QMONS dataset was the first real-world audio dataset for SELD, and the AVE-CL UMONS dataset was its audio-visual counterpart. So while these represented a critical and necessary step away from purely synthetic data, these initial datasets have their limitations. Notably, they used a 2-dimensional circular microphone array, as you can see on the right here, which prevents the estimation of elevation. Furthermore, the sound sources were also placed in a fixed, discrete set of angles, rather than moving continuously as they would in a real scene. So overall, while these datasets are useful, they may not be applicable for real-world use cases. So this brings us to the current gold standard for real-world SELD, which is the SAS dataset series. The release of SAS 22 in 2022 was a major turning point for the entire field. STARS 22 consists of over 5 hours of real, loosely scripted scenes with high precision annotations, captured using a combination of careful human labeling and optical motion capture systems. Now, a key feature here is that because these are natural scenes, the dataset has a realistic long-tailed distribution of events. So for example, you will get far more speech events than a rare alarm event, which is a significant real-world challenge that models must overcome. Then, in 2023, STARS 23 extended this dataset by providing added synchronized 360-degree video data, which established the primary benchmark for today's audiovisual SELD research. So beyond silent microphone arrays, dataset diversity is growing to cover more practical, everyday use cases. A key example here is the wearable SELD dataset. Here, researchers used a head and torso simulator, or HETS, equipped with 24 microphones to record impulse responses. These were then used to synthesize a dataset that simulates SELD from the perspective of a user rather than a static eigen microphone. So this is crucial in demonstrating that SELD is indeed feasible using microphones embedded in wearable devices like our headphones or AR glasses. Taking this a step further, we have the 6 degrees of freedom, or 6DOF SELD. So this addresses the most complex dynamic scenarios where both the sound sources and the listener can be in motion simultaneously. So the 6DOF SELD dataset combines multi-channel audio with synchronized data from motion tracking sensors, providing ground truth velocity and angular velocity. Now this is absolutely crucial for real-world applications like robotics or augmented reality, where the user is continuously moving. And finally, another important gap that was only recently addressed is the environment. Thus far, the vast majority, if not all SELD datasets, consist of indoor recordings. The UNS ESSE23 dataset is the first of its kind, providing spatial recordings collected entirely outdoors. It specifically focuses on anomalous sounds like gunshots and explosions, making it highly relevant for urban noise monitoring and public safety applications. So hopefully they can extend this dataset in a similar manner to STARS, where we have a greater variety of sound event classes for more practical use cases. Okay, so we have our datasets. Now we need to feed them into a model. The next step in our pipeline, as highlighted here, is feature extraction. So this is an absolutely critical step where we transform the raw, complex, multi-channel audio into a structured and informative representation that a deep learning model can better learn from. Now, while some research has explored learning directly from raw audio, most state-of-the-art SELD systems rely on feature engineering. So the goal here is to explicitly extract and embed physically meaningful cues into the model's input. We can broadly split these features into 2 main types. First, spectral features, which describe the acoustic content or the what part of the signal, like its frequency content over time. The second is spatial features, which embed the explicit directional information or the where part of the signal. So let's start with spectral features. The foundation for almost all audio processing is the time frequency spectrogram, which you can see on the left. However, modern systems typically use a more perceptually inspired version, with the most widely adopted being the log-mel spectrogram as shown on the right. So by using the mel scale, we mimic the human auditory system. In other words, we allocate greater resolution to lower frequencies and compress the higher frequency bands. So this is good for detection. It is very effective at discriminating between sound event classes. But it comes with a critical trade-off for SELD. This binning process can merge spatial cues from distinct frequency bands into a single mel band, which can seriously hinder the model's ability to localize, especially in complex scenes with multiple overlapping sound sources. So the next step here is spatial features. So how do we get good spatial features? The choice is almost always dictated by the audio recording format. For FOA recordings, the de facto standard are intensity vectors, or IVs. IVs are a physically grounded feature that describes the directional flow of acoustic energy at each time frequency bin. So the direction of arrival is associated with the inverse of the direction of energy flow. On the other hand, for mic recordings, we rely on interchannel relationships. The most common feature here is the generalized cross correlation with phase transform, or GCC-FET. This method essentially calculates the time difference of arrival between microphone pairs to infer the sound's direction. So in more recent work, more advanced feature sets have been developed. A prominent example is SALSA, or Spatial Cue Augmented Log Spectrogram. So the key idea here is to avoid the MEL spectrogram, and instead SALSA uses log linear spectrograms, which preserves frequency resolution and stacks them with advanced spatial cues derived from the eigenvector of the spatial covariance matrix. So crucially, this design maintains direct TF-bin alignment of spectral and spatial features, which the authors show is key for SELD performance. Now the authors also introduced a computationally efficient version called SALSA Lite. It replaces the costly eigenvector computation with normalized interchannel phase differences. So this makes it much faster and highly suitable for real-time applications, though it is specifically designed for the mic audio format. Okay, so with our features, but as we discussed, SELD datasets are often small and expensive to create. So this makes data augmentation absolutely critical for improving model robustness and preventing overfitting. So the number one challenge in SELD augmentation is that our transformations must be spatially aware. We cannot, for example, apply a random transformation to one channel but not the others. Doing so would destroy the delicate interchannel phase and level differences and potentially corrupt the training process. So generally, it is considered good practice to ensure that augmentations are applied consistently across all channels. So we can categorize these augmentation methods into three main types: spectral-temporal, spatial, and mixture and synthesis. So first, let's take a look at the spectral-temporal domain. These methods are often adapted from image and speech processing. So the most common here are masking techniques like spec augment, which you can see here. It introduces random masks or bars along the time and frequency dimensions. This forces the model to learn more robust and distributed representations rather than focusing on a specific feature. And as we discussed previously, for SELD, it is crucial that the same mask is applied across all audio channels to preserve the underlying spatial cues. Now, other spectral techniques manipulate the frequency content directly. For example, we highlight filter augment, which manipulates the spectral correlation from different acoustic environments by applying random gain offsets to different frequency bands. We also highlight frequency shifting, which simulates pitch shift in the frequency domain by shifting frequency bands up or down. Now, for a category that is highly effective for SELD is spatial domain augmentation. By far the most popular and effective method here is audio channel swapping, or ACS. Based on the physical symmetry of the microphone array, we can systematically swap or permute the microphone channels. For a tetrahedral array using standard FOA or MIC recordings, this can generate up to 8 unique directional configurations from a single recording. In other words, the ACS method simulates rotating the entire microphone array or sound field and adjusts the directional labels accordingly. Now, the most important benefit of this transformation is that it perfectly preserves the underlying acoustic properties of the recording environment, including reverberation, which makes it incredibly effective for training on real-world data. Now, the final category involves creating new samples by mixing or synthesizing them. Mix-up is a well-known technique that linearly interpolates the waveforms and labels of two different samples. A popular variation is spec mix, which performs this mixing in the time-frequency domain. So as you can see in the diagram here, it takes patches from two different spectrograms and combines them. Now this is often preferred as it avoids the averaging of raw waveforms, which could potentially obscure the very class discriminative cues that we want the model to learn. Now, finally, in practice, state-of-the-art systems don't just pick one augmentation, they use augmentation chains, where different augmentation methods are applied sequentially to the input features. Alternatively, as you can see here, different augmentations may be applied to different samples within a single training batch. Of course, designing these complex chains requires significant manual effort and parameter tuning. So because of this, recent research has started exploring automated or adaptive strategies that can automatically find the best augmentation policy for the task. Okay, so we have our data and we've engineered our features. Now we arrive at the heart of the pipeline, which is the deep learning model itself. This is so-called the brain of the system that performs the network inference. The foundational architecture for most modern SELD systems is the convolutional recurrent neural network, or CRNN. As the diagram shows here, it's an intuitive pipeline. A CNN front end acts as a feature extractor, scanning the input features to learn local spatial temporal patterns. This sequence of patterns is then fed into a recurrent neural network, like a gated recurrent unit or GRU, which models the temporal dynamics and context over time. Finally, one or more fully connected layers acts as a decoder, taking this high-level representation and mapping it to our final outputs, the event probabilities, and their corresponding DOA estimates. Now, the very first deep learning approach back in 2015 actually framed SELD as a giant classification problem. It used a predefined coarse grid of directions, and each combination of a sound and a grid location was a unique class. The major drawback, as you can imagine, was that it is very difficult to scale this approach to more sound classes or finer spatial resolution. So the foundational breakthrough came in 2018 with the SELD-NET architecture. SELD-NET introduced the joint classification and regression framework that we see on the right. It keeps the classification for the what, but uses a regression output for the where. So this is the key that unlocked continuous, high-resolution direction estimates and formed the basis for nearly all modern SELD systems. So building on the SELD-NET foundation, modern architectures have evolved for better performance. A very common advancement, as shown here, is to replace the original shallow CNN front end with a much deeper residual network, or ResNet. So this allows the model to learn a far more complex and expressive hierarchy of features directly from the input. Now, in the same spirit, the temporal modeling component has also evolved. The recurrent layers are frequently being replaced by more powerful attention-based modules. For example, the conformal architecture, which combines convolution with self-attention, has proven to be extremely effective at this temporal modeling task. Now, in recent years, the powerful ResNet conformal hybrid, as shown in this diagram, was proposed. Now, subsequently, most, if not all, top-performing DK submissions have adopted this architecture in some manner to achieve state-of-the-art results. So, while there are an increasing number of new architectures being proposed, we want to highlight an interesting type, which is the CST former. So, a limitation of a standard conformer is that it typically flattens the input features, applying attention only along the temporal axis, which can lose a lot of valuable information. Now, if you recall, SELD features are inherently multidimensional. The channel axis encodes spatial cues, the spectral axis encodes acoustic cues, and the temporal axis encodes dynamic cues. So the CST former, or channel spectral temporal former, is a popular architecture that was designed specifically to make full use of this multidimensionality. So instead of flattening, it applies separate attention modules to each dimension independently. By modeling the complex relationships within and between each of these domains, it can extract a much richer representation, often leading to significant performance gains. Now, while end-to-end training is dominant, it's worth mentioning previous modular strategies. So these strategies decouple the SELD task. For instance, on the top here we see a two-stage approach An SED module is first trained, and its learned weights are then transferred to initialize an identically structured DOAE module. So on the bottom, we see another method where we first train independent SED and DOAE models and feed the outputs into a third alignment module to solve the data association problem after the fact. So while this can be effective, they do add significant complexity to the training pipeline, which is why most state-of-the-art systems today favor unified end-to-end architectures. Now, a final key strategy we want to highlight is the emergence of large-scale pre-training. We've seen how effective this is in other domains, such as sound event classification or audio tagging, and is particularly effective for SELD, given that existing high-quality labeled datasets are generally limited in their size and class distribution. So this process involves two stages. First, a large model is pre-trained on a massive dataset. This could be a general-purpose audio dataset like AudioSet, or as shown in the table here, for PSLD nets, a massive synthetic dataset. So the first stage teaches the model a rich, generalizable representation of audio, and in the second stage, this powerful pre-trained model is then fine-tuned on smaller, real-world target datasets. So this transfer learning approach serves as a powerful starting point that often leads to significant performance gains. So, we've now successfully built our model, but now we have to decide what it should predict. And as you will see, how we format the model output is a critical design choice. And this decision will fundamentally determine the complexity of the acoustic scenes that our system can understand. So the initial approach, which was used in the foundational SELD net, is this class-wise two-branch output format. It's rather intuitive. As the diagram shows here, the model has two separate output heads, one for SED, which is a multi-label classification task, and a parallel one for DOAE, which is a multi-output regression task. So the link between them is the class index. If the dog class is active, you look at the dog index in the DOAE branch to see where it is. So while this is a simple and rather intuitive solution, the output format has two major drawbacks. The first and most significant is that it can only represent one instance of each sound class at a time. It cannot handle a scene with two people talking or two dogs barking simultaneously. Second, it is inherently a multitask learning problem. You're trying to optimize two different losses, like binary cost entropy for detection and mean squared error for localization, which often requires careful and complex loss-weight balancing to get right. Now, to solve that multitask learning problem, the ACC DOA format was introduced. It stands for Activity Coupled Cartesian Direction of Arrival, and is a rather elegant solution. It unifies both detection and localization into a single three-dimensional vector for each class. So here's how it works. The direction of the vector encodes the three-dimensional Cartesian DOA, and the magnitude or length of the vector represents the event's activity probability. So as the diagram shows here, an inactive event, like footsteps, is thus a zero vector, while an active event, such as the barking dog, is a vector pointing to the source with a magnitude of 1. Now, the beauty of this is that it simplifies the entire training objective down to a single regression loss, which stabilizes training and improves performance. However, it still only has one vector per class, so it cannot handle multiple instances of the same event. So how do we solve this same class polyphony problem? The breakthrough was the introduction of track-wise or multi-track outputs, famously used by the Event Independent Network, or INV2. Now, the idea is simple. Instead of one output per class, the model predicts a fixed number of independent tracks. Each track has its own full output for both SED and DOAE. But this creates a new challenge, which is track ambiguity. Now, as shown in box 3 here, if the model predicts a dog bark on track 1 and a car on track 2, but the ground truth is car on track 1 and dog bark on track 2, how do you calculate the loss? The network's prediction is technically correct, just in the wrong order. So this is solved using permutation invariant training, or PIT. During training, you calculate the loss for all possible permutations of the tracks, and then backpropagate the gradients only for the permutation that gives the minimum loss. So this forces the model to learn to match its predictions to the ground truth, regardless of the order. And this brings us to the current state-of-the-art format, which is multi-ACC DOA. Now, as the name implies, it is an intuitive combination of the multi-track framework with the efficient ACC DOA vector. And this is the dominant format used by most top-performing systems and has been the output format of the DK Challenge Series baseline since 2022. It also introduced a specific or specialized training strategy called auxiliary duplicating PIT, or ADPIT. So this solves a specific problem. What if you have 3 tracks, but only one active sound event? Standard PIT will match one track to the sound and train the other 2 to output nothing. So this can be a rather weak training signal. So as the figure on the right shows, ADPIT cleverly duplicates the ground truth vectors of active events onto the empty tracks, which are shown by the dotted arrows. So this ensures that all output tracks are matched to a meaningful target, which provides a much stronger, more stable training signal. So this slide here provides a great visual summary of the 4 main output formats we've just discussed. On the top row, we have the class-wise formats, which cannot handle same class overlap. The original 2-branch and the unified ACC DOA. And on the bottom row, we have the track-wise formats, which can handle same class polyphony, which include the track-wise 2-branch and the current state-of-the-art track-wise multi-ACC DOA. So now we've built a full pipeline from data to output. But how do we know if it's any good? So this brings us to the final piece of the training loop, which is evaluation. Once our model produces an output, we need to measure its performance. As we'll see, the way we evaluate SELD has to evolve significantly to actually reflect the true goal of the task. So initial evaluation, used in the 2019 DK Challenge, simply treated the 2 tasks independently. It measured SED using the standard error rate and F1 score, and measured DOAE separately using directional error and frame recall. So this has a critical flaw which fails to penalize data association errors. So the diagram on the right illustrates this problem perfectly. System A correctly detects a child on the left and a cat on the right, and it also localizes them correctly. It gets a perfect score. Now take a look at System B. It also correctly detects child and cat, and it also correctly finds the 2 locations. However, it swaps them, claiming the child is on the right and the cat is on the left. Now, under the old decoupled metrics, System B will also get a perfect score, even though its understanding of the scene is fundamentally wrong. So this clearly showed that we need a joint evaluation metric. So to solve this, the community developed joint evaluation metrics that are now the standard. So the core idea is simple but powerful. A prediction is only considered a true positive only if its class prediction is correct and its predicted location is within a spatial threshold of the ground truth. Now, as the diagram shows, this threshold theta is typically set to 20 degrees. So this joint true positive definition is then used to calculate 4 key metrics: a location-dependent error rate or ER, a location-dependent F-score, a class-dependent localization error, which is the average angular error only for correctly detected events, and a class-dependent localization recall, which is the recall rate of those correctly localized events. Now finally, these 4 metrics are aggregated into a single holistic SELD score, calculated using this aggregation, which allows us to rank the systems using a single number. So the table here shows the SELD metrics for top performing systems on the SAS23 validation set. Now on the far right, you can see the combined SELD score, where lower is better. So looking at these results, we can see some clear trends. The first is a strong preference for the FOA audio format. Every single one of these top systems that outperform the baseline use the FOA audio format. In fact, the DK's baseline results at the bottom of the table also shows that the FOA system significantly outperforms the mic system using the exact same model. So while this is good for offline validation, the mic audio format is generally more flexible for real applications. So this is a potential research gap that future work can explore. Now, another key observation is the large variation in resource usage. If you take a look at the params and data columns, you can see that top systems often use very large models or model ensembles and are trained on hundreds of hours of data. So this highlights an important point. Our current metrics can measure performance, but not training efficiency. More training resource utilization means we incur greater financial and environmental costs. Also, when we compare SELD systems that vary greatly in terms of training resource utilization, it becomes difficult for us to truly quantify the intrinsic effectiveness of each approach. So in other words, it is hard for us to say whether the method proposed is truly effective or merely a result of more training resource utilization. So the table here provides a snapshot of other top performing systems from recent literature outside of the official DK submissions. The trends we observed hold true here as well. We see a continued preference for the FOA audio format and a heavy focus on pushing the boundaries of model architecture. For instance, the CSD former achieves strong performance by rethinking how attention is applied, while the PSLD nets demonstrate the immense power of large-scale pre-training on synthetic data before fine-tuning on a real-world target dataset. So this is by no means an exhaustive list, but it's highly representative of the key research directions in the field today. Alright, welcome back. So now looking at all those results with those massive models and huge datasets, it naturally leads to a critical question. It's great, but can we actually use this in the real world? So this brings us to our next section, the challenges and solutions for implementing SELD in real time. So there is often a significant gap between state-of-the-art models developed in academic benchmarks and the stringent requirements for practical, real-world deployment. This is a quote-unquote reality check for SELD, and the primary constraint here is computational complexity. Top-performing systems are just simply too large and too slow for real-time inference on a typical edge device. Now these devices, whether in a robot, a smart speaker, or wearable headphones, operate under very strict power and memory budgets that these large models would instantly exceed. Now furthermore, what makes SELD uniquely challenging is its reliance on multi-channel audio. We're not just processing one audio stream, we're processing multiple streams and then computing complex cross-channel features, all of which adds a significant processing overhead and latency before the model even sees the data. Now, it's important to remember that it's not just about the model architecture. The entire pipeline contributes to the computational cost. The feature extraction stage, in particular, can be a major bottleneck. Now, for every additional channel of audio, the cost of computing the spectrogram increases. Now, on top of that, SELD requires us to extract both spectral and spatial features, which can double the workload. So this is where using computationally efficient features, like the salsa light set that we discussed earlier, becomes crucial. So ultimately, deploying an SELD system is, at the end of the day, a balancing act. A designer must carefully manage a tight budget of latency, power, and memory, and decide where to spend it, on a more complex feature set, a larger model, or more sophisticated post-processing. So to show you what this looks like in practice, here's a short demo video of a lightweight SELD system running in real time on an edge device.
Zero, zero, 4, 2, 0. 8, 3, 1, 8, 3, 1, 2, 3, 6, 9, 2, 8, 0. 4, 2, 9, 2, 1, 1, 3, 2, 6, 9, 4, 2, 0, 3, 5, 3, 6, 2, 0, 3, 2, 4, 5, 3, 5, 9, 7, 6, 3, 6, 7, 6, 5, 6, 6, 4, 9, 3, 3, 1, 1, 0, 4, 6, 6, 0, 1, 1, 7, 7, 7, 3, 3, 5, 7, 5, 6, 6, 5, 1, 1, 8, 1, 2, 3, 2, 8, 3, 9, 0, 4, 1, 0, 4, 4, 7, 7, 7, 3, 2, 8, 7, 4, 5.
Okay, so now let's move on to one of the most exciting new frontiers in this field, which is multimodal SELD. So the core idea here is that audio, or powerful, is not the only sensor that we have. By intelligently fusing audio with other data streams, we can create a far more robust and holistic understanding of a scene. So the first example we look at is audio motion fusion. So this is essential for 6DOF SELD, where the listener, like a robot or a person wearing a headset, is also moving. So the 6DOF SELD dataset is the key benchmark for this task. So what's fascinating here is how they propose to fuse the data. Sorry. As this diagram shows, they use a multimodal transfer module, MMTM, where the motion sensor data, such as the velocity and angular velocity, is used to excite or modulate the acoustic features. So this is an intuitive way to mimic how the human uses dynamic cues, like small head motions, to pinpoint a sound's location. It allows the model to also learn to compensate for its own movement and distinguish it from the movement of external sound sources. But perhaps the most active area of multimodal research is the natural combination of audio and vision. So this is driven by the fact that the two modalities have perfectly complementary strengths. Now, vision, on one hand, provides incredibly high spatial accuracy, but is limited by occlusions, poor lighting, and a finite field of view. Audio, on the other hand, is omnidirectional. It can hear through occlusions and behind the camera, but it generally has a much lower spatial resolution. So a well-designed audio-visual SELD system can leverage the best of both worlds, using one modality to support the other when it fails, and therefore build a far more robust and complete understanding of the scene. So, how do we fuse them? The first method is an implicit approach using feature embeddings. So as this diagram shows, the idea is to take powerful pre-trained vision networks, like a ResNet50, and use them to extract a dense feature embedding directly from the video frames. Now this embedding captures a holistic representation of the visual scene rather than specific objects. And this visual embedding is then fused with the audio embedding for a final prediction. This exact strategy serves as the official baseline for the DK's 2024 Audiovisual SELD Challenge. The alternative is an explicit approach, using object or pose-based representations. As shown here, you first run a standard object detector like YOLO to find all the objects, faces, or human poses in the video frame. The pixel coordinates of these detections are then encoded into a spatial representation, for example, as a Gaussian map, which is then fused with the audio features. So this can be highly effective, but its performance is completely dependent on the quality and vocabulary of your initial object detector. So in other words, if it fails to detect an object, the SELD system may very likely be blind to it as well. So once you have both your audio and visual feature streams, you need to fuse them. There are several strategies here, the simplest of which is early fusion, where you literally just concatenate the feature vectors together and let the network figure it out. A second method is late fusion, where the visual information might be used as a post-processing step to refine the model's final output. Perhaps the most sophisticated approach, as shown here, is attention-based fusion. Here, you use cross-attention mechanisms to model the deep relationships between the two modalities. So this allows the audio stream to query the visual stream and vice versa. in order to find correspondences and build a much richer fused representation. So as you can imagine, a major challenge for real-world audiovisual SELD is the extreme scarcity of large-scale, strongly labeled audiovisual datasets. One clever way to mitigate this is with data augmentation. So recall the audio channel swapping method that we discussed earlier. That technique can be extended directly into the visual domain in a technique called video pixel swapping, or VPS. In VPS, the exact same spatial transformation is applied to the audio channels, like an 180-degree rotation, is matched with a corresponding pixel-level transformation on a 360-degree video frame. So as you can see in these images, this effectively expands the dataset with new, physically consistent spatial and temporal viewpoints from a single recording. Another powerful strategy is to overcome data scarcity is cross-modal teacher-student learning. The core idea here is to leverage the fact that we have much more audio-only data than audio-visual data. So as this diagram shows, the process has two stages. First, a powerful audio-only teacher model is trained on extensive audio data, both real and synthetic. Then, an audio-visual student is then trained on the smaller target audio-visual dataset. So the key here is that the student's loss function is regularized by the teacher's outputs, which effectively transfers the robust knowledge from the well-trained audio model to the multimodal student, significantly boosting its performance on the target task. And finally, if you don't have enough real data, the simplest method is just to create raw data. So tools like SELD Visual Synth are being developed specifically to generate synthetic visual mixtures that correspond to the spatial audio scenes. So this synthetic audio-visual data can then be used to augment the limited real-world datasets, helping to improve model generalization. Now, the final and perhaps most transformative frontier in multimodal SELD is the integration with large language models, or LLMs. The goal here is to move beyond fixed class outputs such as dog and cats and enable open-ended spatial audio reasoning. So you want to create systems that can answer natural questions about a complex acoustic scene, such as what sound is happening behind the person who is talking. So to achieve this, two primary architectural paradigms have emerged: end-to-end fine-tuning, which deeply integrates the LLM, and modular training-free reasoning, which prioritizes flexibility. So first, let's take a look at the end-to-end fine-tuning approach. The foundational framework here is the BAT model. As the diagram shows, this approach connects a specialized spatial audio encoder directly to an LLM. The audio encoder's output tokens are projected into the LLM's embedding space and acts as a soft prompt. So this entire system is then fine-tuned on a large, custom-generated question-answering dataset. So to make this possible, the authors created Spatial Sound QA, which is the first large-scale dataset for this task. It contains thousands of synthesized binaural audio clips, paired with a huge range of questions, from simple perception such as "is there a dog barking?" to complex multi-hop spatial reasoning, such as "what is the sound on the left side of the dog barking?" Now, the alternative is a modular training-free reasoning system. This approach is designed to avoid the immense computational cost and potential for catastrophic forgetting that comes with fine-tuning a massive LLM. The core idea here is to decouple perception from reasoning. A prime example of this framework is from Siddhartha and colleagues, which focuses on reasoning about moving sound sources. First, a specialized perception module processes the audio to detect events and extract their frame-level spatial attributes. These attributes are then formatted into a structured text representation, such as a JSON object. And this structured text, along with the user's query, is fed to a standard off-the-shelf LLM, which generates an answer without any retraining or fine-tuning. It just simply reasons over the text that is given. Now, perhaps one of the most fascinating findings from this line of research is that language can be used as a form of weaker supervision. As this work demonstrates, it's possible to learn SELD-like capabilities without any of the dense, expensive, frame-level annotations that we've been discussing. By training a model only on scene-level question-answer pairs, such as "is the siren to the left of the dog, the model is forced to implicitly learn how to localize sounds in order to answer these spatial questions correctly. For example, in this work, the author showed that the SELD QA model achieves performance comparable to fully supervised baselines, highlighting the immense potential of language to dramatically reduce annotation costs in the future. Now, other models are focused on creating better representations for these LLMs to reason over. For example, Spatial Clap aims to resolve the content space permutation problem. That is, in a scene with a dog and a clock, how do you bind the dog sound to the left location and the clock sound to the right location? So Spatial Clap does this by learning a single fixed dimensional embedding that represents the entire complex spatial scene. It uses a content-aware spatial encoder to fuse the what and where into a unified representation. And this holistic embedding is powerful for tasks such as spatial audio retrieval, and in the future, it could serve as a much more efficient and comprehensive input for language models. The most recent evolution of this trend moves beyond simple question and answer to full scene description and narration. A system from Microsoft called Sci-Fi is the first audio LLM trained to generate a complete structured text representation or description of the entire acoustic scene in a single pass. So as you can see from this example output here, it doesn't just list the sound events and their 3D locations. It also describes the room's acoustic properties like volume and RT60 and the background noise. It's a truly holistic descriptor aiming to create a machine listener that can describe an environment much like a human would. So now we'll take a short break. We'll come back with the next section. Alright, that concludes our look at multimodal systems. Now let's turn to a few other advanced and emerging topics in the SELD landscape. A major push in the community is towards full 3-dimensional SELD. So far, we've discussed mostly this 2D SELD, which gives us direction in terms of azimuth and elevation. 3D SELD completes the picture by integrating sound distance estimation, or SDE. This provides us a full 3D spatial understanding, letting us know the what, the where, and the how far. So this task is the main focus of DK's 2024 and 2025 challenges. However, estimating distance from audio alone is extremely challenging. If you take a look at the official results from the DK's 2024 challenge, a pattern emerges. On the relative distance error metric, most of the complex submissions actually performed worse than the simple baseline system. Only the top 3 teams managed to achieve a meaningful improvement in distance estimation. So the key takeaway from those results is that for distance estimation, brute force methods such as using bigger models or more data do not seem to work. A likely reason for this is that the input features that we discussed thus far, like intensity vectors or GCC-FET, were designed for directional localization and contain very little explicit information about distance. Now, psychoacoustic research tells us that the primary physical cue humans use for distance perception in reverberant environments is the direct-to-reverberant ratio, or DRR. And this has motivated recent research into designing novel, physics-informed features. For instance, as shown in these diagrams here, our own work has explored integrating explicit reverberation and spatial coherence features, while a related paper explored using signal autocorrelation features. So both of these aim to provide the model with the DRR-related cues that it needs for accurate distance estimation. Now, another major challenge, which is especially pronounced for distance estimation, is the domain shift between synthetic data, often used for training, and real-world acoustics. Data synthesis methods often fail to perfectly replicate the complex, subtle patterns of real-world reflections and reverberation. And since those are the very cues that we need for accurate distance estimation, this domain gap can severely hinder performance. Now, on a forward-looking note, to push the field towards more practical applications, the DK's 2025 challenge has now shifted its focus towards stereo-based 3D SELD. So this is a rather exciting development as it aligns SELD research with the common stereo audio format found in most consumer electronics. Now, a major bottleneck that has always constrained SELD research is the heavy reliance on large, strongly labeled datasets. Curating these datasets, where every sound event is carefully annotated in both time and space, is incredibly expensive and time-consuming. As such, a major recent focus in this field has been on label-efficient learning frameworks. So the goal here is to reduce the dependency on massive labeled datasets. And this has led to two main philosophies. First, self-supervised learning, which learns powerful representations from the abundant unlabeled data. And second, zero and few-shot learning, which enables a model to detect new classes it was never explicitly trained on. One of the most popular self-supervised approaches is masked prediction pre-training. The Wave2V SELD framework is a prime example, adapting the famous Wave2Vec model for spatial audio. So this is a two-stage process. In the first stage, as shown on the left, the model is pre-trained on a massive amount of unlabeled multi-channel audio. It's given a pretext task: predict the content of randomly masked or hidden segments of the input. In order to solve this fill-in-the-blanks task, the model is forced to learn rich, high-level representations of both acoustic content and spatial relationships. In the second stage, this powerful pre-trained model is then fine-tuned on a very small amount of labeled data, where we add the task-specific SED and DOA hits to solve the downstream SELD task. Now, another powerful self-supervised method uses neural blind source separation as its pre-training objective. Here, the model is given only multi-channel mixture signals and is tasked with separating them back into their constituent sources. In order to successfully unmix these sounds, the model must explicitly learn the spatial properties of the scene to distinguish one source from another. And this process forces the model to develop a strong inherent spatial awareness. This learned awareness can then be transferred and fine-tuned for the SELD task, again, requiring very little annotated data. Now, shifting gears, zero and few-shot learning aims to make SELD systems more flexible, allowing them to detect new, unseen classes without being fully retrained. So this is typically achieved by providing the model with either a text description of the new class in zero-shot, or a few audio examples in few-shot at inference time. Now, the enabling technology for this is a model like CLAP, which learns a joint embedding space where sounds and text descriptions have a shared meaning. The key challenge, however, is the assignment problem. If you detect a sound on the left, how do you associate it with the correct text-derived class? So the Embed ACC DOA model solved this elegantly. It's trained to output a CLAP audio embedding directly alongside its corresponding location vector. So this intrinsically links the what and the where, and at different time, the system can simply compare the output embedding for a sound event to the text embeddings of the new target classes and assign the correct label to the correct location. Now, a primary challenge in any real scene is handling a high degree of polyphony, especially when multiple instances of the same class occur simultaneously. As we discussed, our standard trackwise output formats have a fundamental limitation. They have a fixed capacity. If you design your model with 3 tracks, it can never detect 4 overlapping sound sources, even if it hears them. So an emerging solution to this is a paradigm shift towards location-oriented detection. Instead of asking the model to find n number of events, you ask it, for each region in space, tell me what is happening here. So these models partition the 3D spatial field into a grid, and the model will predict what sound classes are active within each grid cell. This location-centric approach theoretically allows the model to handle an arbitrary number of overlapping sources, making it far more robust in environments with unknown and dense polyphony. Now, another major challenge is ensuring robustness to unseen acoustic environments. A model trained perfectly on clean synthetic data will often fail when deployed in a noisy, reverberant real room. and this problem is known as domain shift. In order to solve this, the field has explored various domain adaptation techniques. The goal here is to create a single robust model that can generalize or adapt to new acoustic conditions on the fly, without needing to be retrained from scratch for every new room it enters. Now, this one paradigm for this is meta-learning or learning to learn. Instead of training a model to be good at one specific environment, a meta-learning algorithm learns a general-purpose strategy for adapting quickly. The meta-SELD framework is a great example. It treats each distinct acoustic environment in the training set as a separate task. It then uses an algorithm called model-agnostic meta-learning to find a set of meta-initialized model parameters. This initialization point isn't optimal for any single environment, but it's excellent compromise from which the model can be rapidly fine-tuned to a new unseen environment with just a few labeled samples, and this process is known as few-shot adaptation. An even more dynamic and active approach is echo-aware adaptation. The idea here is for the system to actively probe a new, completely unknown environment without any pre-existing data. So this is a two-stage process. As shown here in stage 1, the system first emits a known sound, like a startup chime, and measures the resulting acoustic echo. This echo acts as a unique acoustic fingerprint of the room, containing rich information about its geometry and reverberation. Afterwards, in stage 2, during normal operation, this echo embedding is then used to condition the feature refinement network. It essentially tells the model, you are in this specific room, so filter out the artifacts accordingly. This allows the SELD system to adapt on the fly to any new space that it enters. So in our final technical session, we'll briefly explore how SELD systems can be integrated with other complementary functions. These integrations aren't just about improving SELD's core performance, they also unlock entirely new capabilities and applications.
In the next section of this tutorial, we will briefly look at how SELD can be integrated with other complementary functions to improve performance and to enable new applications. Sound-source separation can play a vital role in improving SELD performance, especially in scenes with a high degree of polyphony, where multiple sounds overlap. In such cases, sound-source separation can serve as a powerful front end to the SELD system. For example, the top-performing system of the DK's 2023 Challenge adopted this approach. They use class-dependent separation models to isolate specific target sounds and then train the SELD model using the original audio mixture and the separated target features. The separated features act as a strong form of guidance, helping the SELD focus more on the target event. A more advanced strategy performs sound source separation and SELD jointly. In this slide, we present an example using the Deep ASA model. This model first generates an initial estimate for the sound event detection and localization as shown in Net 1. A temporal coherent matching module uses cross-attention to align the DOA and SCD features. These aligned features are then used by the feature fusion block to create a fuse clue. In Net 2, this clue is combined with the original audio features to produce a more accurate and time-aligned output. In the last two slides, we saw how sound-source separation helps SELD handle overlapping sound. But there's more to it. Our environment also shapes how we hear and locate sound, and many researchers use scene or location information to improve sound detection and classification. I will give a short overview on how this field of research has evolved in the last 20 years. One of the earliest works combining classification of scene and sound events was published in 2011. In this study, sound events were used to estimate the sound scene that the sound events occur in. In 2013, a two-stage model is proposed where the scene is first estimated, and context-specific sound events are then selected for the detection of sound events. Sound event detection with adaptive background modeling to improve sound detection in a dynamic, noisy environment was also used in robotic applications. In 2015, Liu and colleagues presented a model that first estimates a scene and then identify dominant sound events, which are then used to infer non-dominant sound events. In 2016, Emoto proposed to model acoustic scene as a probabilistic mixture of acoustic subtopics. For cooking scene, acoustic subtopics can be preparing ingredients and frying ingredients, and each subtopic is modeled by the probabilistic distribution of sound events. In 2019, Song estimated a scene by recognizing distinctive sound events that constitute the scene. Each audio sample is represented as a bag of instant, where each instant is a high-level representation of a sound event within a scene. Fun fact, a lot of research work on cattle sound event detection was also proposed in 2019. By 2019, one of the first multitask learning or MTL models for acoustic scene classification and sound event detection was published. Initially, this model performed worse than standalone models. Within the next 2 years, many researchers addressed some of the issues of MTL by introducing trainable weights and coupling metrics to better control the training of ASC and SED tasks of the MTL model. Fixed scenes containing events that do not exist were also employed in training. Soft scene labels from an ASC teacher model are also used to guide the scene layers of the student MTL model. In 2022, Howe proposed a relation-guided ASC model to exploit the scene-event relation for improved recognition of scenes and events. Combining weak and strong labels of sound events was also shown to improve the performance of multitask learning of ASC and SED tasks. Temporal attention mechanism to select informative frames from the audio data was also found to be beneficial to MTL training. In 2024, Zhang proposed using attention mechanism to extract information from both local and global features. In addition, this model employs a soft parameter sharing mechanism between the SAD and the ASC tasks to facilitate effective interaction of information between the scene and sound events during training. And finally, in 2025, our lab has published a context-based SELD in AES 2025, which will show that environmental context can be used to improve both SED and DOE estimation. A context-aware SELD system can be developed by integrating ASC and SELD. Using the core ideas that certain sound events are more likely to occur in specific environments, an ASC model can be first used to identify the scene, such as the urban street or an indoor room, and then use the environmental context to guide the SELD model. In hearable devices, this means that these devices can intelligently adjust sound levels or active noise cancellation, allowing critical environmental sounds such as approaching vehicles or alerts to pass through. This integration enhances both safety and situational awareness of its users. Combining ASC and SELD can lead to a model having high complexity. Since ASC can be a valuable front end for improving downstream tasks, researchers have explored low-complexity ASC models to make integration with other modules more computation efficient. In fact, the DCASE challenge has featured low-complexity ASC as a dedicated task since 2020. The objective of this task is to develop a model to classify 10 sound scenes of 12 European cities recorded by different devices. This task provides a rich set of resources and benchmarks for developing models that balance performance with computation efficiency. Our approach to ASC focuses on keeping the model low in complexity, simple to train while maintaining comparable accuracies. Our model operates with just 10.9 million max and requires 117 kilobytes of parameters. Unlike many recent submissions to DCASE, our approach is the only network apart from the DCASE baseline that does not apply knowledge distillation and does not use an ensemble of models to improve its performance. This design approach not only simplifies training, but also achieves a 6.7% improvement of accuracy over the DCASE baseline in 2025. This brings us to the end of the technical sessions of our tutorial. Let's summarize what we have covered so far. In summary, SELD is a powerful technology for advanced environmental acoustic intelligence, combining the what of detection and where of localization. We saw that building a SELD system involved several key design choices: the input audio format, the feature extraction techniques, the deep learning backbone, and output format. And critically, we learned that SELD evaluation must be joint, ensuring a prediction is only considered correct if both the location and the class are correct. Looking forward, the field is moving beyond localization towards a more holistic understanding of acoustic scenes. This includes achieving a full 3D awareness by integrating distance estimation and, most significantly, the trend towards multimodal SELD to build a richer understanding of the environment. The integration with large language models is also transforming SELD into an interactive, language-native task, creating systems that can truly reason about what they hear. This rapid progress wouldn't be possible without communities such as DCASE and L3DES, which foster a collaborative research environment that continues to spear exciting and innovative advances across the entire SELD pipeline, as shown on the right side of this slide. We have now come to the end of this tutorial. Thank you for your attention.